If you think about it, the universe is kind of like a massive, impossibly complex computer. And all of physics, modern engineering, literally our entire understanding of reality is built on a very specific source code. But this code isn't written in ones and zeros. It's actually written in highly precise, internationally agreed upon measurements. So welcome to our explainer on the International System of Units, the SI system. Today, we are decoding the Universal Operating System. So let me ask you this. How do we actually measure reality? Now, obviously, that's a rhetorical question, but I want you to really think about the completely mundane units that we all just take for granted every single day. A meter, a second, a kilogram. You might think a second is just, a quick tick on your watch. But without extreme, truly microscopic accuracy in how we define that tick, everyday technology, like the GPS in your phone, would be entirely useless. Navigation, telecommunications, global finance, they would absolutely crash without this underlying precision. Okay, let's dive into this. We're going to run a quick system boot sequence here and go through the core modules of our measurement system. First up, the rules of reality. Then, defining length through light, followed by time and atomic clocks. After that, the standard of mass, and finally, precision and unit conversion. All right, kicking things off with Module 1, the rules of reality. Now, what's really interesting about this is how we actually organize the absolute chaos of physics. Back in 1971, by international agreement, the scientific community established a small, invariable set of base quantities. We're going to be analyzing three foundational ones today: length in meters, time in seconds, and mass in kilograms. Basically, every other physical measurement out there, speed, power, pressure, you name it, is derived right from these three. The whole trick is making sure these standards are accessible to everyone and, most importantly, completely invariable. Moving right along to Module 2, defining length through light. It's crazy to think about, but our human demand for invariability forced us to literally zoom out to the cosmos just to define a simple meter. The evolution of this is wild. Back in 1792, the newborn Republic of France defined the meter as exactly 1/10,000,000th of the distance from the North Pole to the equator, which is a grand, poetic idea, but yeah, a bit hard to measure perfectly. So by the late 1800s, we shifted to a physical object, a platinum iridium standard meter bar kept securely in a vault near Paris. But even a chunk of solid metal can change slightly over time or, be destroyed. So in 1983, the scientific community took a massive leap. They scrapped physical objects entirely and redefined the meter by the distance traveled by light in a vacuum.
And that brings us to the magic number: 299,792,458 meters per second. That is the exact speed of light in a vacuum, a constant denoted by the letter c. The modern meter is now permanently anchored to this ultimate invariable cosmic speed limit. Officially, a meter is defined as the length of the path traveled by light during a time interval of exactly 1/299,792,458 of a second. By anchoring our human measurement to a fundamental constant of the universe itself, the standard can literally never degrade.
All right, that brings us to Module 3, time and atomic clocks. So, we've locked down space. Now let's lock down time. Any standard of time basically has to answer two questions. When did an event happen? And what is its duration? To give you a sense of how our timekeeping has evolved to answer this, there's this wild historical oddity from the French Revolution era, a 10-hour watch. In 1792, when they were proposing the metric system, they actually tried to redefine the day into 10 decimal hours. Spoiler alert, it obviously didn't catch on. For centuries, our timekeeping relied on the rotation of the Earth. But the problem is, Earth's rotation isn't perfectly smooth. It wobbles. It's affected by tides and winds. We realized we needed something way, way better than just the spin of our planet.
So, to find that perfect consistency, we zoomed all the way down to the microscopic quantum level. Here is the modern definition of time. 1 second is the time taken by exactly 9,192,631,770 oscillations of the light emitted by a cesium-133 atom. We now govern time using the invisible, ultra-precise ticking of an atomic clock. And to put that into perspective, these atomic clocks are so incredibly consistent that 2 cesium clocks would have to run for 6,000 years before their readings would drift apart by more than a single second. That is mind-blowing precision.
Next up, Module 4, the standard of mass. We've covered length and time, so now let's explore the standard that defines all mass in the universe. For a very long time, this was based on the international 1 kilogram standard.
It's a highly polished cylinder made of a platinum iridium alloy, exactly 3.9 centimeters in height and diameter, kept under lock and key in a vault near Paris. For well over a century, humanity completely relied on accurate copies of this exact physical object to calibrate scales worldwide. If you bought a kilogram of flour at the store, its weight authority was ultimately derived through this long chain of comparisons going right back to that one metal cylinder in France. And this brilliantly illustrates the stark contrast between the macroscopic and microscopic worlds in physics. On one hand, we have our human-scale physical standard, the 1 kilogram cylinder. But for measurements on an atomic scale, a metal cylinder is just way too clunky and imprecise. So scientists use a second atomic standard, the carbon-12 atom, which is assigned a mass of exactly 12 atomic mass units. By using this, scientists can experimentally determine the masses of other atoms relative to carbon-12 with truly incredible pinpoint precision. And finally, Module 5, Precision and Unit Conversion. Okay, so we've established the theoretical definitions of these base quantities, but practically speaking, how do we do the math and convert between units? Let's walk through a technique called chain link conversion. I personally love this because it is such a satisfying algorithmic process. Step 1, you just write down your original measurement, let's say 2 minutes. Step 2, multiply it by a conversion factor equal to unity, or 1. Because 1 minute equals 60 seconds, the ratio of 60 seconds over 1 minute is just 1. Step 3, we multiply our 2 minutes by that 60 seconds over 1 minute. The minute units mathematically cancel out. They're literally struck through, leaving us with exactly 120 seconds. In these conversions, units obey the exact same algebraic rules as variables and numbers. It keeps your math perfectly clean and error-free. So the crucial point here is this underlying concept of scientific honesty. Whenever you do these calculations and report your data, your final answers should never, ever over-report your precision. This rule of scientific honesty is completely governed by the concept of significant figures. Let's look at a quick comparison to clear this up because it trips people up all the time. Take a measurement like 3.56 meters. That has 3 significant figures and 2 decimal places. Now compare that to 0.00356 meters. This one also has exactly 3 significant figures, even though it stretches out to 5 decimal places. You really cannot confuse significant figures with mere decimal places. When you plug numbers into a calculator, it might spit out 8 completely meaningless decimal digits. Scientific honesty means you have to round your final result to match the least number of significant figures in your original data. Those extra calculator digits, they aren't real precision. They are just digital noise. As we wrap up this explainer, I want to leave you with this absolutely fantastic quote from the writer Eden Philpotts. He said, "The universe is full of magical things, patiently waiting for our wits to grow sharper." Think about it. Our entire mastery of measurement, redefining the meter by the eternal speed of light, or tracking time by the quantum hum of cesium atoms, that is exactly how we sharpen our wits. Physics is the gateway to uncovering these magical, hidden truths of reality. Which leaves us with one final provocative thought. We've decoded the basic operating system of reality. But what magical things will our precision uncover next? Because whether we look way out into the vast cosmos or zoom all the way down into the tiny quantum realm, measuring reality is really just the very first step in understanding it. Thank you so much for joining me on this X-Planner. Keep asking questions and keep your wits sharp.